Good morning. Today we are going to talk about computational fluid dynamics lab. The objective of this lab is to learn how to do numerical simulations using ANSYS. ANSYS has a couple of different CAD softwares included in the package. One of them is Design Modeler, which is the oldest one, and we're going to use this one to do the training for you. And you are welcome to use this one or any other CAD software to build your geometry. And eventually we're going to use this this CAD model, put it inside a fluid simulation software called Fluent, and then do aerodynamic analysis on it. For the next lab though, you are going to take these results, put it in a static structural model is to do a structural analysis, and that will be posted as a separate video in its own folder on Blackboard. To understand what we're doing today, we need a little bit of background about aerodynamics. So, on any object that is passing through a fluid, inside the fluid is immersed in a fluid and moving through it, there are 4 different forces that is exerted on any object. Thrust force is usually provided by some sort of an engine. Of course, if you are using a glider, you don't really have a thrust force, but whenever you have an engine, whenever you have a power source that is pushing you through forward, essentially, you have the thrust force. And weight force, that is because of the mass of your system. But the two aerodynamic forces that we are concerned with are lift and drag. Lift is a force that is normal to the direction of the flight, and drag is a force that is pulling you back, that is tangential to the direction of flight or movement. Lift and drag are also very important forces in designing a car. We understand the drag comes into play when you are dealing with fuel efficiency, and it has become even more important when in the era of electric cars. And lift, its direction is usually downward on cars to help with traction. Okay, so our goal in this lab is to do an aerodynamic analysis on a flat plate specifically. Okay, let's learn a little bit of nomenclature. So on an airplane or a car or any object that is passing through any sort of fluid, we have a geometry called an airfoil. This airfoil is a 2D cross section of your wing, your body, your object, whatever that is, right? A 2D cross section. And there are a couple of important parameters here, like the thickness of this airfoil, the connection between the beginning point, which is the leading edge, and the end point, which is the trailing edge. That's called the chord line. How curved your airfoil is. All of these things are going to contribute to our design target, which is to maximize the lift in aircraft specifically, maximize the lift over drag ratio. We are not going to talk about all of these things, that the contributions of the curve and whatever to the lift to drag ratio. But one thing we have to learn from this slide is this angle of attack. So again, angle of attack is the angle between the chord line, this line that connects your leading edge to the trailing edge, and the direction of flight. Right? This is one thing that you want to learn from this slide. Okay? So we understand the forces, we know this nomenclature, we understand what angle of attack specifically is. And eventually we want to know how to analyze aerodynamic performance of a vehicle. To do so, we need to come up with non-dimensional parameters that are related to lift and drag. Why do we want to use non-dimensional parameters? To be able to compare the performance of different aircrafts at different conditions, at different sizes, with different engines and whatnot. But when you use dimensional analysis, when you non-dimensionalize the parameter, it will free you to compare different scenarios with each other. Okay. How do we calculate these non-dimensional parameters for lift and drag? These non-dimensional parameters are called lift coefficient and drag coefficient. Lift coefficient, C of L, is equals to lift divided by a parameter called dynamic pressure, which is the kinetic energy of your air, of your liquid or whatever, fluid in general. And it's calculated as by multiplying 1/2 by density by the square root of flight velocity, moving velocity. And the drag coefficient is calculated by dividing the drag force by the dynamic pressure multiplied by the area, span area that's exposed to this movement of air. Okay? So our goal in this lab is to calculate the lift and drag coefficients for different angles of attack to do an aerodynamic analysis and eventually find lift versus angle of attack, lift coefficient versus angle of attack curve at different velocities. Okay, and we're going to do the same thing for drag coefficient versus angle of attack. But our focus here is on lift versus angle of attack. As you can see, there is a linear side to it. So for smaller angles of attack, lift changes linearly with angle of attack. Lift coefficient specifically changes linearly with angle of attack, meaning that when you change the angle of attack, you will be able to find the lift slope very easily, and there's a linear pattern. This is what you want to find in your simulation, this specific part of the graph. And then we want to get to this region, which is called the stall region. This happens, the stall region is essentially the maximum lift coefficient you're going to get, and then we're going to have a reduction in lift coefficient as you increase the angle of attack. The reason we have this reduction is because of this adverse pressure gradient, which you have seen in your heat transfer course if you have passed a heat transfer course, or maybe fluid mechanics or aerodynamics if you are an aerospace engineer. But we don't really need to focus on these. We just want to find this specific plot for our flat plate. We want to start from a negative angle of attack, which is going to give us zero lift. It's called zero lift angle of attack. It's usually a negative angle of attack. For symmetrical airfoil, it's usually zero, right? This angle of attack. So you assign a negative angle of attack in your simulation, and you increase your angle of attack as you go to find this line, and then to find the stall condition, you want to go ahead with a higher angle of attack to make sure that you have reached the stall condition. So this is what I expect. This part of the graph, up to this part, is what I expect to see in your lab reports. The main question is how to do this though. We are going to, the next step for you is to watch a tutorial that I'm going to post, and will be posted with this recording. And in this tutorial, you are going to learn how to run the simulation for one angle of attack. And then I'm going to show you how to change the angle of attack, how to give it different angles of attack, and run the simulation again. And eventually, we want to find the CL versus alpha, CD versus alpha, and another graph that is called drag polar, which is CL versus CD, angular lift coefficient versus drag coefficient. You want to include all of these in your report, as well as a couple of heat maps. And we did talk about heat maps in previous week's lecture.